The Arctic Ocean has undergone unprecedented changes over the past several decades, driven by a combination of anthropogenic climate forcing and inherent climate feedback mechanisms. Among the most visible and significant indicators of this transformation is the rapid retreat of Arctic sea ice, particularly during the summer months. Since satellite records began in 1979, the minimum sea ice extent has declined by approximately 40%, with much of the perennial multi-year ice being replaced by thinner, seasonal first-year ice. This transition marks a fundamental shift in the Arctic's climate regime. One of the most critical processes amplifying Arctic warming is the ice albedo feedback. Albedo refers to the fraction of solar radiation reflected by a surface. Sea ice, especially when covered with snow, has a high albedo and reflects most incoming solar radiation. In contrast, open ocean surfaces absorb the majority of incident sunlight due to their low albedo. As sea ice retreats, it exposes more dark ocean water, which in turn absorbs more heat, further accelerating the melting of surrounding ice. This feedback loop was originally hypothesized in the 1960s and later demonstrated in early climate models, but only in recent years has it been confirmed through direct satellite observations and advanced modeling. The study by Pistone et al., 2014, Observational Determination of Albedo Decrease Caused by Vanishing Arctic Sea Ice, represents a major step forward in quantifying this feedback. Using satellite data from the clouds and the Earth's Radiant Energy System, (CERES), along with sea ice concentration data from passive microwave instruments, they provide direct observational evidence of the darkening effect due to Arctic sea ice reduction and the consequent increase in absorbed solar energy. Complementing this large-scale observational work, Kashiwase et al., 2017, with the study Evidence for Ice-Ocean Albedo Feedback in the Arctic Ocean, Shifting to a Seasonal Ice Zone, investigate the mechanisms and impacts of ice-ocean albedo feedback within the context of a shifting Arctic climate. Their analysis focuses on how heat input through open water fractions drives both seasonal and interannual variability in sea ice retreat. By combining satellite data with a simplified ice-ocean coupled model, they demonstrate that divergent ice motion in early melt seasons plays a key role in triggering large-scale feedback processes that amplify ice loss. Together, these studies highlight the central role of albedo feedbacks in Arctic amplification and provide a robust framework for understanding ongoing and future changes in the region's climate system. To quantify the impact of Arctic sea ice loss on the region's reflectivity, or albedo, Pistone et al. Employed a novel combination of satellite datasets. Specifically, they utilized radiation measurements from NASA's CERES instrument, which captures the amount of solar energy reflected back into space, alongside sea ice concentration data derived from passive microwave satellite sensors. These datasets span multiple decades and provide a comprehensive view of both the Arctic's energy budget and its evolving ice cover. The researchers focused on the Arctic region north of 60 degrees north and analyzed both clear sky and all sky albedo conditions between 2000 and 2011, with extensions back to 1979 based on inferred relationships between sea ice cover and albedo. They divided the Arctic into subregions to account for spatial variability and seasonal changes, allowing them to better isolate the influence of sea ice loss on planetary albedo. A key finding was a clear, non-linear relationship between sea ice concentration and albedo. Areas with more ice reflected significantly more sunlight, while those with reduced ice showed a pronounced drop in reflectivity. Importantly, this darkening was not offset by increased cloud cover, indicating that cloud albedo feedbacks are not compensating for the loss of reflective ice. Over the period from 1979 to 2011, the Arctic's all-sky albedo decreased from 0.52 to 0.48, corresponding to an additional 6.4 watts per square meter of solar energy being absorbed into the Arctic Ocean system. When averaged globally, this represents a radiative forcing equivalent to roughly 25% of the warming impact from the rise in carbon dioxide during the same period. These findings offer direct observational confirmation of the albedo feedback mechanism and emphasize the Arctic's role as a significant amplifier of global climate change. Kashiwase et al. Explored a key question in Arctic climate dynamics. How strongly does heat absorption through open water drive sea ice loss, and what are the feedback mechanisms involved? Their study provides quantitative evidence for what is termed the ice-ocean albedo feedback, the process where melting sea ice increases the fraction of exposed dark ocean surface, which absorbs more solar radiation, further enhancing melt. To investigate this feedback, the authors combined satellite data from 1979 to 2014 with a simplified coupled model of the sea ice and upper ocean. Their focus was the Pacific Arctic sector, a region that has experienced the most extreme reductions in summer ice cover in recent decades. Satellite datasets provided daily measurements of sea ice concentration, surface heat fluxes, and ice drift velocities. Using these, they conducted a detailed heat budget analysis that separated the energy absorbed by open water from that absorbed by ice-covered areas. One of the central findings is that the heat input through the open water fraction, what they call Q, explains the majority of both seasonal and year-to-year variations in sea ice melt. They found strong statistical correlations between Q and actual ice melt volume, showing that this absorbed energy is the dominant driver of ice retreat in summer. Crucially, they identified a mechanism that acts as a trigger for this feedback. Divergent ice motion in the early melt season, often caused by shifting wind patterns, creates open water gaps that expose the ocean to increased solar radiation. This early season divergence, which has nearly doubled in magnitude since 2000 due to the increasing mobility of thinner, younger ice, significantly enhances the subsequent melt by amplifying the ice-ocean albedo feedback. To validate and explore this process further, the authors developed a simplified two-dimensional model coupling sea ice concentration with upper ocean temperature. The model simulations reproduced the observed evolution of ice retreat and confirmed that divergence-induced openings in the ice pack substantially increase oceanic heat uptake, especially in recent years. In extreme melt seasons, even modest early-season divergence led to large-scale feedback-driven ice loss. Overall, Kashiwase et al. Demonstrated that the Arctic's transition to a more seasonal, mobile ice regime has increased the sensitivity of the system to this feedback. Their work underscores the importance of ocean-ice interactions in shaping the trajectory of Arctic sea ice in a warming climate. Together, the studies by Pistone et al. And Kashiwase et al. Provide a comprehensive, multi-scale perspective on the role of albedo feedback in the rapidly changing Arctic climate system. Pistone et al. Offer a top-down, satellite-based assessment of the large-scale radiative consequences of sea ice loss, while Kashiwase et al. Present a more process-oriented view, examining the dynamic mechanisms that trigger and amplify these changes. Pistone et al. Showed that the Arctic has undergone a significant planetary darkening due to sea ice retreat, corresponding to an increase of solar energy absorbed into the Arctic Ocean. Remarkably, this energy gain is comparable to a quarter of the global radiative forcing attributed to increased atmospheric CO2 over the same period. The authors emphasized that this observed albedo forcing is substantially larger than previous estimates, highlighting the importance of using direct satellite measurements to capture the full radiative impact of sea ice loss. Moreover, their analysis demonstrated that cloud cover changes have not compensated for this loss in reflectivity. By examining both clear sky and all sky conditions, the study showed that the darkening trend persists under all sky conditions and is consistent with a largely unchanged cloud field. This reinforces the conclusion that Arctic darkening is primarily a surface-driven phenomenon linked to shrinking ice. Importantly, the study explored the broader implications for climate feedbacks, calculating an upper bound estimate of the albedo feedback parameter associated with Arctic Ocean ice loss, which is comparable to, or even exceeding, the total global surface albedo feedback values used in current climate models. This suggests that models may be underestimating the strength of the surface albedo feedback from Arctic processes alone. In sum, their findings provide robust observational evidence that Arctic sea ice decline constitutes not just a regional change, but a global radiative forcing agent, one whose magnitude rivals that of major anthropogenic greenhouse gases. Kashiwase et al., meanwhile, identified a crucial trigger that activates and intensifies the ice-ocean albedo feedback, divergent ice motion early in the melt season. This mechanical spreading of the ice opens gaps in the ice cover, allowing solar radiation to penetrate and warm the ocean surface. They demonstrated that the feedback loop initiated by this process explains much of the observed variability and long-term decline in summer sea ice extent. Notably, the feedback's intensity has increased since the early 2000s, coinciding with the Arctic's transition toward a seasonal, thinner ice cover that is more responsive to atmospheric forcing. The two studies converge on the conclusion that Arctic sea ice loss is not just a passive response to warming, but an active contributor to further climate change through powerful feedbacks. By combining observational data, empirical models, and satellite-derived energy budgets, both papers underscore the Arctic's role as a hotspot for climate amplification. Looking ahead, these findings point to key areas for future research: improving model representation of sea ice dynamics and feedbacks, refining predictions of regional and seasonal variability, and integrating more detailed oceanographic processes into coupled models. As the Arctic continues to shift toward an ice-free summer state, understanding and monitoring albedo feedbacks will be essential for anticipating their broader climatic impacts.